welcome back. So, in the last lecture, we were discussing about convolution of two Riemann integrable function, which one can view this as a product in the space of Riemann integrable function. What we have seen is that if f and g are two Riemann integrable function, then f convolution g is also a Riemann integrable function. And then we proposed that convolution actually increases the regularity of the function in a sense that if I am taking two Riemann integrable function, then their convolution is going to be a continuous function irrespective of whether f and g are continuous or not. So, that is what the proposition we have stated in the last lecture, and what we saw is that if f is a continuous function, that means one of the f or g is a continuous function, then f convolution g is also a continuous function. That is what we had seen in the last lecture. Now, we would like to do this for if f is an arbitrary Riemann integrable function. Okay. So, in order to get this result that f convolution g is a continuous function, we will be needing the following lemma. Let f k be a sequence of functions such that goes to 0 as k goes to infinity, and f is also a Riemann integrable function. Then f k convolution of g of x converges to f convolution of g of x for all g Riemann integrable. Moreover, this convergence is uniform. Okay, so let us get the proof of this lemma. The first, observe that if f and g Riemann integrable, then f convolution g of x modulus is less or equal to supremum over all y belongs to 0 to 2 pi mod of g of y, and then 1 by 2 pi integral 0 to 2 pi f of y dy. That is fairly simple, because f convolution of g at x, this is equal to 1 by 2 pi integral 0 to 2 pi f of y g of x minus of y dy, Now, if I take the mod and then if I push the mod inside the integral by triangle inequality, we are going to get this. Now, you pull out the maximum value of g, this because g is a bounded function. So, this is lesser equal to supremum over all y belongs to 0 to 2 pi mod of g of y, then what it remains is 1 by 2 pi 0 to 2 pi mod f y dy. Now, clearly f k convolution of g of x minus f convolution of g of x, by linearity of the integral, what we have seen, this is f k minus of f convolution of g of x. So, therefore, by above observation, mod of f k convolution of g of x minus is lesser equal to supremum of y belongs to 0 to pi mod g y 1 over 2 pi f of y dy, and given to us in the hypothesis of the lemma that this converges to 0 as k goes to infinity. Therefore, and this is a finite number. So, therefore, this converges to 0. That means, f k convolution of g converges to f convolution of g for every x. As you can see that here in the right hand side, it is independent of x. So, this convergence is uniform. So, once we have that, then now get back to the question what we have asked about whether f convolution g is continuous or not. Now, in this you take f to be an arbitrary Riemann integrable function, then we have learned that there exists a sequence f k of continuous function such that f k goes to 0 as k goes to infinity. So, therefore, what we have got is that mod of f k convolution of g minus f convolution of g of x, this goes to 0 uniformly by our lemma. Now, f k convolution g is a sequence of continuous function, because we have seen that the convolution with a continuous function irrespective of g is a continuous function. Therefore, now a sequence of continuous function converging uniformly to a function, then that function limit function has to be continuous. So, then this f convolution g is continuous. So, that proves that if we have f and g any two arbitrary Riemann integrable function, then f convolution g is a continuous function. That is something important which we will be using quite often at a later stage. Okay. So, now let us compute some convolution. Let us take the example. Let f tilde of x, I am defining that f of minus of x, where f is 2 pi periodic and defined on minus pi to pi. So, what we can see is that we want to find f convolution of f tilde, we know that this is going to be a continuous function and hence Riemann integrable. Now, if we compute the Fourier transform at n, then this is going to be, we know that this is f hat at n and f tilde hat at n. Now, f tilde hat at n, if we are taking, then this is equal to 1 by 2 pi integral minus pi to pi f of minus of x bar e to the power minus of I n x dx, by making a change of variable x going to minus of x, and then if we take the conjugate outside the integral, what we are going to get, this is minus pi to pi f of x e to the power minus of I n x dx whole bar. So, this is nothing but f hat of n bar. Therefore, this will implies that f convolution of f tilde hat at n, this is a positive number mod of f hat of n square. Okay. So, now let us do example 2. So, fundamental object in the study of Fourier series, as we have seen, is the function e to the power I n x. So, now if we take f of x e to the power I n x and g of x is e to the power I m x for some n and m positive non-negative integer or integers n and m, you can take it to be z. So, now f convolution of g at x, this is going to be 1 by 2 pi 0 to 2 pi, then this is e to the power I n x minus of y e to the power I m y of d y. Now, this is equal to e to the power I n x is independent of y, we can take that out, divided by 2 pi 0 to 2 pi e to the power I m minus of n y d y. We know the orthogonality relationship of e to the power I m. So, now this is equal to, if m is equal to n, then this integral becomes 1 2 pi divided by 2 pi. So, this is e to the power I n x if m is equal to n, that means, if f is equal to g, otherwise 0. So, this is in a sense is giving the orthogonality of the e to the power I n x g x. If I am convolving with f these two function, then I am going to get, only it is going to survive if m is equal to n, otherwise it is not going to survive. So, then let us define a trigonometric polynomial p of x. This is equal to summation over alpha of n e to the power I n x, where this mod n is lesser equal to n. That means, the sum is minus n to n. P is called a trigonometric polynomial of degree n if either alpha n not equal to 0 or alpha minus of n not equal to 0. That means, the highest n for which this alpha n coefficient is not equal to 0. This is a trigonometric polynomial which plays a very fundamental role like the polynomial plays in C01. So, now if we have a trigonometric polynomial, then it is natural to calculate p hat of m. Now, this is going to be p is a finite sum. So, you can take the sum outside mod n lesser equal to n, then 1 by 2 pi factor is there, then this is 0 to 2 pi, alpha n can come out, it is a scalar, and then what we have got e to the power I n minus of m x dx. Now, look at this. If our m is such that mod m is greater than capital N, then n minus m can never be 0. Therefore, this is 0 if mod m is greater than n. Now, if mod m is less than m, then this there is a scope that n can be equal to m. Whenever n is equal to m, we are going to get this to be 1. If n is not equal to m, then we will get 0. So, therefore, this is going to n is equal to m, that means, this is alpha m if mod m is lesser equal to n. Therefore, the Fourier series of p is summation. Now, here p hat of m e to the power I m x, that is the Fourier series. As you can see that if mod m greater than capital N, then this is going to be 0. So, this is becomes a finite sum. And now, p hat of m, what we have calculated is nothing but alpha m and e to the power I m x. Now, this is nothing but the same as p. So, that is quite interesting. And now, similarly, if I have a p of x, this is equal to summation over mod n lesser equal to n alpha n e to the power I n x, and q of x, this is equal to mod n lesser equal to sum n beta n of e to the power I n x. Then easily you can see p convolution of q of x, this is going to be summation over mod n lesser equal to n, and we can make it m mod of m lesser equal to sum m alpha n beta m, then e I n x convolution of e I m x. That is already we have computed. This is a little abuse of notation. So, this is the function e I n. So, now this what we have seen is that this is going to survive if n is equal to m. So, this you can see that this is going to be mod n lesser equal to sum n sub naught alpha n beta n, where n naught is equal to minimum of n and m. So, that is what the convolution of the two trigonometric polynomial will look like. Now, another example, let us take f is the constant function 1 and g is any arbitrary function. Then f convolution of g of x, this is equal to 1 by 2 pi, f is a constant function. So, this is equal to f of x minus of y is equal to 1. So, this is g of y dy, this is for every x. So, this is going to be constant. So, now it is natural to ask that if we are saying that convolution is some sort of a product on the space of Riemann integrable function, then does it have an identity? That means, does there exist, the question, does there exist a h belongs to pi periodic Riemann integrable function such that f convolution of h is equal to f for all f Riemann integrable. Now, suppose such an h exists, then what is going to happen? F convolution of h hat at n, this is equal to f hat at n, because f convolution of h is equal to f. Therefore, left hand side becomes f hat of n, h hat of n is equal to f hat of n. Now, if we get a function, Riemann integrable function, whose Fourier coefficient is never 0, then we can divide that f hat of n both the sides, right. And what do we have such a function? Now, if I take my f to be indicator function of minus of 1 1 of x and then extend it periodically by the period of 2 pi defined on minus pi to pi. So, this is the function what I am. This is 0, then there is a copy of this like this function. This is the periodic function. What we have seen earlier is that f hat of n is equal to some constant times 1 by pi sin n by n if n is not equal to 0 and is equal to 1 by pi if n is equal to 0. So, this shows that for such a f, f hat of n never vanishes. Therefore, from this equation we can now, this star holds for this f also and f hat of n is never 0. So, from star we get h hat of n is equal to 1 for all n in Z. Now, what is our h? We are saying that our h is a Riemann integrable function. Then Riemann-Lebesgue lemma says that if h is a Riemann integrable function, then h hat of n goes to 0 as mod n goes to infinity. But here we are claiming that if such an identity exists under convolution, then that identity's Fourier coefficient is going to be the constant function 1, which cannot happen, because this violates, this is a contradiction because of Riemann-Lebesgue lemma. As it says that h hat of n must go to 0 as mod n goes to infinity. Okay. So, we are talking about the Riemann-Lebesgue lemma. So, let us get some application of the Riemann-Lebesgue lemma. All of us we know that 0 to infinity sin x by x dx, this is equal to pi by 2. Now, I am going to give you a proof of this fact using Riemann-Lebesgue lemma. So, now let us define g of x is equal to 1 by sin x by 2 minus 1 by x by 2 for x is in minus pi to pi, and then the periodic function. Now, as you can see that this g is continuous everywhere except at x equal to 0. Now, at x equal to, when x tends to 0, then this exists. So, thus g is continuous, because as you can see, if x is in minus pi to pi, then x by 2 is in minus pi by 2 to pi by 2, and only problematic point for where sign is going to vanish is when x is equal to 0, because x by 2 is going to be in minus pi by 2 to pi by 2. Therefore, g is a continuous function. Now, if g is a continuous function, then let us minus pi to pi g of x sin n plus 1 half dx. Now, sin n plus 1 half is equal to sin n into cos x by 2, sin n x into cos x by 2, and plus cos n x sin x by 2. And then we know that in Riemann-Lebesgue lemma says that minus pi to pi f of x sin n x dx goes to 0, as well as cos n x dx goes to 0, because e to the power I n x goes to 0, and these are all the for real valued function f. So, these are the real part and the imaginary part. Example, this is sin n plus 1 half of x by sin x by 2 dx minus pi to pi sin n plus 1 half of x by x by 2 dx. Okay, so, we will continue with the computation of these two integrals, and we will see what values it is going to take as n goes to infinity. Thank you.